I've been in networking for over a decade and decided to make some content to try to help others understand this industry. So far, we've looked at how traffic flows between two endpoints that are directly connected together. And then we looked at how traffic flowed when we connected those two endpoints to the same switch. So now we're going to take it a step further and talk about what happens to allow endpoints to talk to each other when they're on different layer 3 networks. And to do that, we need a router. So let's start with the topology that we had before with the two endpoints connected to a switch. And we're going to make some modifications to this just to hopefully make sense of what we're doing and why when we start moving these connections. So we have PCA and PCB. The MAC addresses on these, we're going to simplify a little bit. So instead of having all 12 characters, we're just going to call the MAC address of PCA just A, and the MAC address of PCB is just going to be B. As we add more MAC addresses into the topology, we're going to do that same thing. Just for simplicity, there's no real reason to sit there and call out all 12 characters. The other thing that we need to do is connect the two PCs to different switches. So now we have two switches here, one directly connected to PCA, and then a separate switch is connected to PCB, and then that allows us to connect the router in between them. But to make sure that we don't get confused between which switch is which, we're going to name one of the switches A. So we're going to talk about switch A, and that's the switch that PCA is connected to. And then we're going to have switch B, and that's the switch that PCB is connected to. So now we can connect the router in here in between these two switches. So from left to right, we're going to just look at the physical topology. So PCA is connected to switch A on port 1, and then port 2 of switch A connects to port 1 of the router. Port 2 on the router will connect to port 2 of switch B, and then port 1 on switch B connects to PCB. So that's our layer 1 topology. Those are the physical connections. So now we need to get some addressing in here for the router. The router has two interfaces there, and so we need some MAC addresses. So the MAC address for port 1 on the router is just going to be C. Like I said, it's still 12 characters. We're just going to simplify it. And then port 2 on the router is going to be MAC address D, still just simplified there. The next thing we need is some layer 3 information. So the router itself functions at layer 3, which means that it's going to separate these networks. So each interface on our router needs to be in a separate network, and then any endpoints that are connected downstream of that interface, they also need to be in the same layer 3 network as that router interface in order for them to communicate. So we can leave PCA in the 1.1.1.0/24 network. So we're not going to change that IP address. The IP address of PCA is going to remain 1.1.1/24. And then we're going to make the interface on the router, interface port 1, we're going to give that an IP address of 1.1.1.254/24. Now these are then in the same network because it's a /24 network. So now we need an interface or an IP address for port 2 on the router. So we're going to give that interface an IP address of 2.2.2.254/24. And when we did that, we actually just introduced a problem because the IP address for PCB, it's connected off port 2 of the router, but its IP address was still 1.1.1.2/24. So that's actually an IP address that's in the network of port 1 on the router. So we need to change that IP address. So we're going to update the IP address of PCB, and it's going to be 2.2.2.2/24. And now it's part of the network that the port 2 of the router is part of. All right, we're almost done with this setup. We need a little bit more information here to make this topology work, and that is that the PCs themselves need to be configured with a default gateway. So the default gateway is what the PCs use or any endpoint for that matter, that's what they need to have a default gateway configured so it knows where to send traffic when it's trying to communicate to devices that aren't on the same network as itself. We'll look at this more in detail through this example, but that's the purpose of the default gateway. So for PCA, its default gateway is going to be 1.1.1.254, which happens to be the IP address of port 1 on the router. That's where it's connected. And then the default gateway for PCB is 2.2.2.254. Also happens to be the IP address of the port 2 on the router. That is not a random chance. That is what we need because that router is responsible for communicating between networks here. So we'll look at that in a moment. So we're finally done with the setup, and now we can start looking at how these devices work together to get traffic from PCA to PCB. We're going to look at what switch A does with the traffic, what the router does, what switch B does with the traffic, and the PCs themselves. Hopefully we're kind of familiar with how they process the traffic at this point. So in our example, once again, PCA wants to send a message to PCB. So we have our message there, and we're going to pick up this example at layer 4, where this message is now a layer 4 segment, and it's being passed down to layer 3, which is the network layer. So PCA has to add a layer 3 header with the layer 3 source and destination addresses. All right, so PCA is the source because it's sending this traffic. So the source IP address is going to be 1.1.1.1. That is the IP address of PCA. And it's trying to send this to PCB at layer 3. So the destination IP address is 2.2.2.2, which is the IP address of PCB. Now that the router has, now that the segment has its layer 3 header, it's a packet. And now we pass it down to layer 2. Now, an important thing here, remember the router has separated this topology into 2 different layer 3 networks, and this separation also divides the layer 2 domain. So PCA is not able to talk directly to PCB at layer 2, and that is really important to understand here, because when we start building the frame, that comes into play. So when we start building the layer 2 header here, PCA knows that it is the source, so it puts its own source MAC address there because that's the layer 2 source is MAC address A. But now it's layer 2 destination. Remember, it can't talk to PCB at layer 2, so it doesn't know about MAC address B. So what it has to do is figure out what is the layer 2 destination for me to talk to something on a different network. And that's where the default gateway comes in. So at this point, PCA, it needs to get traffic to its default gateway at layer 2 so the default gateway can forward that over to PCB. Now, in order to do this, PCA has to consult a table, and that's called the ARP table, the Address Resolution Protocol table. What this table does is it maps layer 3 addresses to layer 2 addresses. So PCA has an entry in its ARP table that says IP address 1.1.1.254 is mapped to MAC address C. MAC address C is the MAC address of port 1 on the router. That's also where the 1.1.1.254 IP address exists. So that makes sense with our topology. Those 2 addresses are the same interface. So what PCA needs to know is, what is the MAC address of my default gateway so that I can send traffic at layer 2 to my default gateway so that the default gateway can forward that traffic at layer 3 to its destination. So now PCA has enough information to build the rest of the layer 2 header. It puts MAC address C as the layer 2 destination. Now it's done with the layer 2 header. It's now a complete frame. And this frame is converted to layer 1 signaling, and it is sent to switch A. So now switch A receives these electrical signals or whatever the signaling type happens to be. It converts those back into bits, reconstructs the frame, and it looks at the layer 2 header and sees that this frame has a destination MAC address of C. So it has to consult a table to figure out, where do I send this? And just like when we looked at a PC to PC communication, when there's a switch connected, the switch has to look in its MAC address table. So this switch, for the example, it has two entries here. The MAC address table, it maps MAC addresses to interfaces, and it knows that MAC address A is connected off interface 1, and MAC address C is connected off interface 2. So the switch has everything it needs to know in order to forward this frame towards its destination at layer 2. So the switch converts this back into whatever the physical signaling is and sends it out port 2 towards the router. Well, now the router receives that signaling information, converts it to bits, reconstructs the frame, and it looks at the layer 2 header. And the router sees that the layer 2 destination is MAC address C, and that happens to be the router itself. So the router knows that this frame has reached its layer 2 destination, so that header can be removed. Next, it looks at the layer 3 header. The router sees that the destination IP address is 2.2.2.2. Well, that IP address is not on the router itself, so the router is not the layer 3 destination for this packet. So now the router has to figure out, where do I need to forward this packet so that it can reach its layer 3 destination? And so once again, it has to consult another table. This table is called the routing table. So the routing table maps networks to interfaces, and it tells the router, in order to reach a specific network, send it out this specific interface. So this router has a routing table with two entries for this example. There's one network, which is the 1.1.1.0/24 network, and that is connected off port 1 or interface 1. And then it also knows of the 2.2.2.0/24 network, and that's connected off port 2. So now the router knows, in order for me to forward this packet to its layer 3 destination, I have to send it out port 2. The challenge here is that the router has already removed the layer 2 header, so this packet is sitting at layer 3 on the router. So the router has to send it back down the OSI model and has to send it back to layer 2, then layer 1 before it can be sent out. So for it to forward it to layer 2, it needs to reconstruct the layer 2 header. The router knows, based off its routing table, that it's going to send this out interface 2. And interface 2 has a MAC address of D. So the router can reconstruct the layer 2 header and say, my source MAC address is going to be D because that's the interface I'm sending it out. But now the router needs to figure out, what is the destination MAC address going to be. So just like before, when PCA, when it had to look in its ARP table to figure out what MAC address do I need to send this to in order to reach the IP, the router has an ARP table as well. And in its ARP table, it shows, again, it's mapping IP addresses to MAC addresses, so layer 3 to layer 2 mapping. It shows that IP address 1.1.1.1 is mapped to MAC address A, and that's the entry for PCA. It knows of that because that's connected on port 1. And it also knows that the IP address of 2.2.2.2 is mapped to MAC address B. It knows that because MAC address B and PCB is connected off port 2. So after the router consults its ARP table, it now knows at layer 3, if I'm trying to send this to a destination IP address of 2.2.2.2, I need to send it to a destination MAC address of B. So now the router can reconstruct the layer 2 header appropriately and has a destination MAC address of B. It converts this down to layer 1 to whatever signaling type it is to send it over to switch B across port 2. So now switch B receives this. Again, gets whatever that physical signaling is, converts it to the bits to reconstruct the frame. And switch B, it looks at the layer 2 header and it sees that this has a destination MAC address of B. So just like switch A, and just like we saw in the other examples, the switch has to consult its MAC address table. So in the MAC address table, switch B has two entries. there is an entry that says that MAC address B is connected to interface 1 and that MAC address D is connected off interface 2. And those happen to be the connections for PCB and port 2 on the router. So switch B knows that in order to send this to MAC address B, I have to forward this frame out interface 1. So switch B forwards it out interface 1, and PCB receives that physical information, converts it to bits, reconstructs the frame, and looks at the layer 2 header here and sees that this frame has a destination MAC address of B. Well, PCB looks at its own MAC address and says, hey, I have MAC address B. So it has reached its layer 2 destination at this point. So PCB can remove the layer 2 header, and then it begins inspecting the layer 3 header. So it looks at the layer 3 header and sees that this packet has a destination IP address of 2.2.2.2. Well, PCB happens to have that IP address, so this packet has reached its layer 3 destination. So PCB removes that header and is left with that message, the segment that was originally sent from PCA. We have this layer 4 segment, and then the rest of the processing happens all the way up through layer 7. So there were several tables that we discussed in this example, and I want to just kind of review those real quick. That the MAC address table is what maps the MAC address to an interface, and that's used for layer 2 forwarding. And that's critical for the switches to know how to forward that traffic. The other table that we talked about is the ARP table. And this one can be a bit confusing because it maps layer 3 and layer 2 together. When reconstructing that layer 2 header, devices need to know if I'm trying to send this packet to a specific layer 3 address or IP address, what layer 2 or MAC address do I need to put on that frame? And the ARP table is what provides that translation. Another thing to mention is that ARP tables are only used for IPv4. There's a different way this happens with IPv6, but there still is a table that maps layer 3 to layer 2. And this is one of the things that was very challenging for me to understand is with this ARP table and the interaction with the default gateway. When I first started getting into networking, I thought that the default gateway was the layer 3 address that an endpoint would send traffic to when it tried to communicate off its network. But then I had to think about it a little bit more, and if the endpoint sends it to that layer 3 address or IP address, then there's nowhere else for it to go. So the default gateway, the reason that we need to know the IP address of the default gateway is so that in the ARP table, we can map that to a layer 2 address or the MAC address, and that's what's reachable. So in order to send traffic off of your local network, you need to know the default gateway, not because you need to send traffic to the IP address, but you have to be able to look up that IP address in the ARP table to figure out which MAC address do I need to send traffic to get off my network. So that is, to me, that was a very challenging concept. The last table that we talked about was the routing table, and this one is what maps the networks to interfaces. And that is how the router is able to send traffic between networks and communicate off of its own local network and send traffic for endpoints off its own local network. So understanding these tables as well as the headers associated with it, it's critical for building and operating networks.